Okay, about myself. I'm Manuel Scholz from Dresden, from the group behind Andreas Pfitzmann. These are the same guys who implemented the Java Anon proxy. You may have heard of it, the JAP. I'm not involved in any JAP programming, but I have recently started to think about implementing the Dining Cryptographers network. It is also from David Schaum, and okay, so finally we can start. So Dining Cryptographers network, David Schaum proposed in 1881 the mix cascades implemented in the Java Anon proxy, and in 1885 to 1988 the Dining Cryptographers protocol, which is an anonymous protocol for a closed group network. So if you have a closed group of people, then they can communicate to each other anonymously. Some boring introduction, table of contents. So about the introduction, what is Dining Cryptographers and how does it work and what are the basics behind it? So in the introductional example from David Schaum, he proposed a dinner where, as example, 3 cryptographers having a nice meal, and after they had their meal, they asked themselves the question, was the meal paid by one of them, or was the meal paid by the, as example, the government, because they were told that the meal was prepaid. So the question is, did any of them has paid for the meal, or did none of them has paid for the meal? And it isn't the question who of them has paid for the meal. They respect their each other's privacy. So they said, okay, I'm only interested in whether one of them has paid the meal. This is the introduction example. So they came up with a protocol, and in basic, each one exchanged a key with each other. David Schaum said, okay, they just flip a coin, and one of them remembered the key, and the other remembered the inverse key when adding keys together. In case of a coin flip, it is just like the same value. So in a coin flip base, it is a GF2. Okay. So if you add head and head together, you get a tail, and if you get head and tail together, you get a head. So the neutral element is the 0 is the tail, and the minus key AC and the key AC is the same in this example. Okay, basically they exchange with everyone else a key. I'm a bit out of order, sorry. And each participant calculates the sum of each keys he has exchanged. So Alice calculates key AB plus key AC and adds the message it wants to send. In this example, it adds a 1 if it has actually paid for the meal, and it adds a 0 if it doesn't have paid for the meal. The same goes for Charlie and for Bob. And finally, they all announce all their sums, and all sums are summed up together again. And now you can recognize if Charlie gets the inverse element of Alice in its key, then this key will cut each other. So here you have the sum of all sums, and then what you get finally is all keys will cut each other out. So you get the sum of the messages. Which means if any one of the 3 said 1 as their message, they get as a sum 1. And if no one said 1, they get as a sum 0. And because the meal could not have been paid by 2 people, let's assume this, this here as a result shows up a 1 if any one of them has paid for the meal. Okay. Why it is secure? Remember the one-time pad. You probably have heard of it. It's just if you have a message and if you have a key and you add them both together, then the key will hide the message. So you cannot get to the message if you don't know the key. Just remember this. We look at the output of the 3 participants. Each of them is a message together with some independent chosen keys, which are themselves also a one-time pad, but they actually hide the message. So if Bob only sees this sum, then it doesn't learn anything about the actual value of Charlie. So it doesn't know whether Charlie sent a 1 or 0, so it doesn't know whether specifically Charlie paid for the meal. And even if you try to calculate some intermediate values from the value Bob knows, as example, he knows the key exchange with Charlie, and try to calculate something like he takes his output and adds only the 1 key to it, then always he get some kind that looks like the random the one-time pad. So this is as example for 2 values he can calculate. David Charm has proven this in his original paper. So if Bob looks at anything that gets published in this network, he doesn't learn anything about the individual messages sent from Charlie, Alice, and Bob. Okay, so to summarize a bit, to fasten a bit up, we just talked about the sender anonymity, which means that you don't know what message specifically is sent by one participant. So nobody knows what exact value M. Charlie or M. Bob or M. Alice is. And it also provides a receiver anonymity because the messages are published to everyone. So everyone gets every message, and so nobody knows who is the actual receiver of a message, if it actually has a receiver and it is not broadcasted for all anyway. So this is the summarize of the Dining Cryptographers protocol original proposed by David Charm. And he only thought about one message. Well, it's a start. We have only one message and that's it. And now I want to talk about when we put this into a stream of messages, into a chain, what we have to do is maybe we introduce some problems about this. So how to go from just one message, publishing one, into a chain of messages. What do we get? What do we need to do if we want to do this over time? Okay, I thought about, we have some rounds where messages are posted, so each round. Each round are separated by so-called ticks where the round ends. This is just some definition. And in each round, what do we have to do? We have to get a list of all people currently still participating in the network. This means the original paper also only thought about a static number of peoples in the network, and nobody can join or leave the network. And I extended this a bit to say, okay, you can join later on and you can leave the network. So in each round, we have to know who is currently participating in the network. Then, of course, we have to prepare the message to send to everyone. Then everyone has to get the final result, the broadcast result. If we don't have a transport medium that already does the broadcast for us, then we have to broadcast the messages somehow. And the last thing is we have to make sure that everyone gets the message. I come to this a bit later when I show some idea of an attack. So it is not enough that you try to broadcast it to everyone. Everyone has to be sure that everyone else got the message. Okay, a bit about the protocol that is behind the Java client you have probably all started by now. Okay, we have a server. I thought about central server. It makes things easier. The server can be does not have to be trusted, so the server can be untrusted, but all the server does is disturb the network and not break the anonymity. Then we have all the clients. Okay, first one, get participant. We need the list of all participants. Then we calculate the message by adding all the keys. Next, we send the message to the server. Straightforward, we receive the message, the final round message from the server. This is a bit later because every other client has to send its parts before the message can be calculated. And finally, we get the confirmation that everyone else got the message. Okay, no rocket science, just a bit more graphical than I just told before. So about the last thing, which means the make sure that everyone else got the message. if you don't do this, then an attacker could modify, as example, could modify messages to specific clients and look for the outcome and say, okay, these clients reacting in a different way, or even block messages to specific clients and see whether the communication goes on. So, and there are several solutions in the research about how to make sure that messages get distributed and not altered and so on. And there are Byzantine agreement protocols. There's actually an implementation named GNU DCN from Leipzig. He implemented a Byzantine agreement protocol to make sure that the message gets distributed. Then there can be trusted third parties to verify that the message is okay. Group signatures can be made so that no one can forge a message, or something like anonymous signatures. And a much easier way proposed, I think, in 1993 by Andreas Pfitzmann was the so-called DC Plus network, where you just mangle the message of the last round in the current round. So if an attacker distributed these different messages to some clients, then in the next round the whole network will break, because some clients will mangle the wrong message into the next round, and the sum doesn't sum up to anything useful. So, and this is of course also easy and fast. Okay. About bad clients. This is maybe the biggest problem about Dynamic Cryptographers network. That is very easy to disturb a network if you're a participant. Just send in random stuff, and the network shut down completely, because if, as example, Alice sends some corrupted data, some random data, and everybody adds this together, then they are not able to tell, okay, this was Alice, because every output of every client look like random data anyway. So there are two different kinds of clients that could disturb the network. There are broken and malicious clients. The broken clients are the easier ones. As example, if you fail to send a message to round, then you could say, okay, the server locks out any client that didn't send the message. So we have already established a dynamic joining and leaving the network. So just if you fail to send a message until the timeout, you get locked out. And of course, in the classic IRC channels or other group network things, there are things like ban list, reputation systems, and so on that can be ported to the domain. Okay, the malicious clients are the more interesting ones. There's an anonymous reservation scheme together with trap messages to handle clients that try to send, as example, random data instead of the correct sums of the keys. And it's described in this paper, which is actually the paper behind the lecture that Andreas Pfitzmann gives, and it's really good described there. I'll take a short summary about the reservation scheme. Okay, let's say you don't publish the real data in each round, so you don't add your message M Charlie, which is the real data, in any round. But instead you send in a reservation block, which is parted into so-called slots. So this is a slot, or this is a slot, here's as example. So, and you set everything to null except one block you want to send a message in. You choose this from random. And this block could, example, look like you have a collision, so-called collision counter, because later on the message adds up together. We remember all messages end up added together. So if you add this block together, then you get this number is increased if someone else also tried to send on this block to 2 or to 10. And here you have some number of bits where, as example, could encode a length of the message you actually want to send. And then you have a separated service, I call it chunk service, nevertheless, where you have chunks where you can place your actual message into. And so each client, if it sees, okay, here's a reservation, and there's a collision count of only 1, so there's no collision when trying to reserve something, to resolve something, then all clients knows, okay, in chunk 23, there's a message with this length, okay, and then additionally I send my my summed up keys to the chunk 23. Summary. Okay, round message means reservation slots. Yeah, you have to choose the chunks at random, so you can recognize some patterns. So if, as example, if one client every time uses slot 1, then it's easily recognizable when he wants to send something. Okay, as a bonus that we didn't have before, is you can encode the length, and you can have some kind of dynamic length in this. So, and then if you have an anonymous reservation scheme, you can place trap messages. So you reserve blocks, and you can and you don't send actually sensitive data in the actual data block. And later on, you can check if someone tries to disturb your message. The attacker doesn't know that you just sent a trap. You can ask for disclosure. You can say, okay, I want to see who sent the message to this anonymous block. I will talk about later. I will later talk about how to disclosure messages on demand. Okay. I think the bonus is a copy and paste error from the last slide. Okay. Key exchange. You may have noticed that I proposed that everyone exchanges keys with everyone else, and this should raise a bell in your head. What? If we have, say, 1,000 people, then we have 1,000 versus 1,000 key exchanges. Everyone exchanges keys with everyone else. How does this work? Okay, it's Diffie-Hellman. For those who don't know Diffie-Hellman, just to recapture, the server or some central place publishes a prime number and a generator on the prime. And then Alice and Bob chooses a random secret, and they calculate the exponent of the generator versus their secret, modulo the prime number, and they publish this value. And then each other can use the published value from the other and calculate the shared secret. So the nice thing about this is that you only have to publish values, and if you have 100 people publishing their public value, then you can automatically
Ministry of Information stellt ab sofort eine Mitfahrbörse bereit. Bitte tragt freie und gesuchte Mitfahrgelegenheiten in die ausgehängten Listen ein. There's a list to organize arranged lifts at the Ministry of Information. Please use the list if you can offer a ride to somewhere or if you're still looking for one. Thanks.
Okay. So finally, you can instantly exchange secrets with all other 99 people if you have their published values. So we degrade the problem of exchanging secrets with 100 different people to fetching their published value. Okay, so Diffie-Hellman. Some more advantages. We don't need some kind of direct client-to-client communication. We only need some communication, get me the published value from this. We have a complete key graph. So David Schaum made some things about how we can reduce the key graph to some subset and still get a bit of anonymity left and so on. And I just said, okay, shut it, complete key graph, so we don't have any problems with attacks in this case. So, and the distribution is easy. It's an asymmetric scheme. You know, the published values are open for anyone. And of course, we don't want to exchange one-time pad keys in this way because they are very lengthy. So we want to exchange seeds for random number generators. And unfortunately, when we exchange seeds, then you can later on prove that you have a specific key generated by publishing the seed, because it is hard to calculate a seed to a given random sequence, but it's easy to calculate the random sequence. So by introducing the seed algorithm, I get a problem here, but it isn't really a problem because Alice and Bob could have exchanged a real random number for the one-time pad. And they don't even have to tell anyone that they did. They just add the real random key and the other add the inverse. And so if someone later on came and say, okay, please prove me that you really have generated this out of some seed, then he can just say, no, I don't have to prove because I've used a real one-time pad. Okay, demonstration. Let's see whether any one of you were able to join my chat. How do I end this? No. Escape? Escape. Okay. Okay. Then where do I get a web browser here? It's a nice window manager. What? Okay. Where on the English keyboard is the tilde? Openings. Okay. So. So okay, I wrote two applications to start. I first wrote a chat client for this. I was searching for an application that don't have such an impact on the fact that you just publish a message to everyone every round. So if you want to have, I think the browser doesn't accept Java applets, maybe. So can I get a command line client and try the Java web start from there? Okay, thank you. So I tried to find applications, and the Dynamic Cryptographers network already does distribution to all. So this is for free. If you use the Dynamic Cryptographers protocol, you always get distribution to all. So I looked for applications where this is a feature and not a bug. And one is, as example, the chat, because of course in a chat everyone wants to see what message you said. Okay. I'll use Java Web Start so you'll get the stuff in your cache anyway. No, it's only yes, so this one. Okay. So, and chat has also an good feature that you don't have to exchange large binaries or large amount of data. The chat is only some. Do you agree? No, of course. Full access to the. Oh, nice. Okay. Oh, that's cool. I'll create a new key. So there are the chat client supports GPG. You can run it without having GPG installed, but if you have GPG installed, then you can verify the published Diffie-Hellman value from the other side. And I've just created it without a password. Okay. Oh. Sorry. Okay, this pop-up says it all. Without GPG, you will not be able to verify other participants' keys, so you're not immune to man-of-the-middle attacks. So this is the chat client. Oh, whoa, I've never seen so much people in my chat. Great, welcome. So okay, so here on this side, you have the list of all people who are currently in the chat, and this is a public information. So I've even included the IP address, and I already got 2 people complaining about publishing their IP address when they log into my server. So they don't want me to know their IP address logging into my server. And here, okay, you get some things here. And okay, it works like a normal chat, except that you can here choose your nickname in this. That appears an example. I can use things like, yeah, maybe there was some outdated client out there. I've changed the version of the client very often in the last 2 or 3 days. Not all are compatible. So anyway, the idea is you can enter, here you can enter a nickname at the bottom, and it is guaranteed that any one of them could have sent the message in this way. So if you send a message, my hello isn't gone through. Okay, it's my first field test. All the tests were about 4 people in the network, or 3 people. So it's probably this broken message here what I sent. So if you send something here, then you cannot be a so as example, if I now send something like GRMML. By the way, these names here, pre-generated, are from the top 1,000 list of baby names in the last years in Germany. It's really crazy how people name their children. Oh God. Okay, it looks like my chat isn't really stable when more than, say, 2 people are online. About 80% of the code is written in the last 3 days with about 2 liter of mate intus. So don't expect much stability. Yeah. Okay. Broke message, yeah. So a broken message occurs as example if you log out from the chat without really logging out, but with killing your process. Then it could be possible that your Java process is killed just before you were able to send your current round message. And as I told you before, every one of the participants add another piece of the resulting message together. And it's not possible to reconstruct the message if one piece is missing. This isn't possible. This is a one-time pad. Or pseudo one-time pad. So if someone logs out before being able to send for the current round, there will be a broken message, and it is not possible for the remaining participants to get to the message. Okay, so chat a bit, no problem. I wrote a second application, and this is the maybe more interesting application. At least I like it more. This is the DC Wiki, which is an anonymous distributed wiki. The current wiki implementation is about 150 lines of Java code, would be maybe 5 lines of Python code. And so don't expect much from the structure and the look and feel and so on. The wiki pages are just HTML code, so please welcome. I'd like to see some cross-site scripting here. before the talk ends. So, okay, yeah. Ah, maybe the bottleneck is my server at home, the Eigenheimstraße. Yeah, okay. Yeah. Yeah, so the broken messages is probably because you were not able to upload the data because the server is too slow. Yeah, anyway. The wiki just uses the same engine beyond. And here, as example, you see here the login Eigenheim wiki, which is a wiki server I run localhost on the machine at Eigenheimstraße. And the idea is that you download your local copy of your wiki at localhost, start it on localhost, then you got some participant in the network in your wiki at localhost, and all edits you do in your local wiki will be distributed in the network, of course, to everyone, so you get a distributed wiki, and nobody will be able to tell who posts this edit currently. So you got an anonymous wiki. Yeah. So, okay, it should work, and now we should get some wiki in here. No. Yeah, here, the wiki. Okay, now let's try to browse to our local URL. Localhost 9454. This is actually what you get when you enter wiki on your mobile. 9454. Okay, so this is the main page of the wiki, and yeah, just some ideas about this, propaganda for the talk, and okay, then you can try to, as example, go to some new page, foobar, and now create foobar. Yeah, whatever. So, and now this message isn't inserted into the wiki right now, but it is sent to the network, and I hope the message gets through, because we expected some problems with messages going through. Broken message. Damn it. Sorry? Yeah, the last thing I try to implement is an LOA protocol to resend the message like Ethernet, to resend the message if it doesn't get through. It is coded but not tested yet, so I didn't want to include it into the protocol right now. But of course, this has to be made sure that you try to get your message through. So unfortunately, this didn't work, so I'll try it again. Second try, last try. Hello, Ficken, kill you. Yeah. There's a myth that, oh, another wiki? No, another wiki? Nice. But no message from me? That's really strange, because I don't get any broken message, so it should get through. Anyway, what I wanted to show you is, no, that was a broken message. What I wanted to show you is that it is just currently using the normal chat, or the chat is using the wiki, or how do you say it? So if you say something like foobar, where's the pipe on the English keyboard? Here. No. Yeah, really nice. Okay, so I'm sorry. So my poor machine at home get denial of service attacked by some chatters. Funny, I'm using it. Actually, this is probably the reason why, because nobody there don't exist any Dunning cryptographers implementation currently out of the wild that is really used. There exist some implementations of some students in their master thesis or so, but they're cool. These are probably broke. Someone logged in with a client running the reservation scheme I showed you before, probably. And this is the reservation scheme block, because just before the talk I switched back to the plain posting messages because it was a bit more stable. So please don't use outdated clients, don't use the chart directly, use the Java Web Start. So, okay. How could it is? So unfortunately you don't see the wiki to work. Coders needed. The project is just about to start, and the idea would be that you distribute the pages all around, and then everyone get their pages localhost. So first, you can make closed group wikis, so you can make wikis that are only known by a closed group, and you can make anonymous wikis where nobody knows what any other people says. Okay, so for the demonstration, didn't work everything. Oops. Try to get all of the slides. Something about here. No, this was before. Yeah, key exchange, demonstration. Okay. Some attacks against the protocol. The original protocol is pretty stable. It is really a good anonymous preservations, but now I introduced some new things into the protocol, like dynamic changing of people in the network, or like the time idea. So there are some additional attacks possible. The first are called the classical timing attack. So we have to think about the attacker could be able to know when in the round people send its message. So it sees, okay, Alice is sending at the very end or at the very beginning of the round. So things like this could happen. If here's a question posted and Alice sent the question just before the round ends, and then Alice sends its message just after the tick, and this time span is too short for people to react to the message, and someone said, oh, no, he sucks. So an attacker could know, okay, this wasn't Alice, because Alice could at first time here know what this message was, maybe except if Alice was the asker anyway. And the attacker can link both messages together. Then he knows, okay, he knows something about the anonymity set. He knows this wasn't Alice. So and this is an attack against the anonymity feature of the network. And yeah, one solution could be, as example, if the server returned the message of the round after the client has sent. So then you just cannot answer to the message of the last round. You can only answer to the message of the round before the last round. So you just delay the message for one round. This is a really clever solution, but, well, this way you get the message a bit delayed. Another nice side effect is that you can use the client-only to server communication stuff known as firewall-proofed, because you only do submits to the server and then get something as return. So another attack, this was actually a successful attack against the Java Anon proxy, is a political attack. So if the people from the government rings at your door and say, get me the data also. So we currently, in my scheme, we have a centralized server. So this is a single point of failure, some kind of. And we have in Germany just passed a law about data retention, where you have to store communication data. Of course, it doesn't make any sense in the Dunning cryptographers network, but still that is a problem for people who want to set up a server. Oh, I have to do some stupid data retention stuff, and I have to make resources available for this. And there could be a warning lawyer threats. There are already very much in Germany. You get a letter, sounds very ugly, okay. In your chat something happens and so on. There could be crypto bans like in Russian. I think it's Russian, don't know. So what could be a solution to this? Why do we need a server at all? So maybe we can get rid of the centralized server, so we really have only clients participating in the network. And this actually could be done, because everything the clients has to do is publishing some value in the internet. So, and you can use your MySpace account, you can use your talk page in Wikipedia, some PHP BB forum, you can even print it on the newspaper and other people scan it in. So you just have to be able to publish some information. And then every participant collect the information from every other participant, sums up the stuff, and get the current round message. So, and the login and logout could also be done by some ways already done in some closed group users things. So this is a really nice idea, because this completely invalidates the data retention idea. So because we don't have any server, we only have clients. Okay, yeah, boo. Okay, I've talked about the disclosure thing, that in the chat message scheme, someone says, okay, I want this message to be disclosed. And David Schaum by itself already thought about how to disclose a message, and he just says, okay, everybody signs his messages, and then you publish your signature, and then you can verify that you use the correct round key. So if anyone signs his own exchange round keys and you get all round keys from everybody, you can just reconstruct the M Charlie, M Alice, and M Bob separated messages. So, and I propose a different scheme I'm calling Watchman scheme, which is some kind of, okay, n predefined watchmen can work together. So we have, as example, Dickens and Elisa, which plays watchmen in a cryptographers protocol. They don't have to be part of the original people. Then the client split their round keys into the n parts and then send each part to someone. And in the case of disclosure, the watchman publishes the parts. They can be reconstructed. So when I'm talking about split round keys, I don't mean the first 100 bit goes to and the second 100 bit goes to, because then the watchman learns something about the actual data. They learn a part about the key. And in the research paper, there's already a protocol for how to split data, how to share data, secret sharing, which is used here. I'm going a bit faster because first, this isn't really interesting for the current audience. I think you are not so interested in how to disclosure the data. And, well, just math. So, okay, how it works, we have Dickens and Elisa, and you send your parts of the round key. So this is a part of your splitted round key. This is another part. You send them to Dickens and Elisa. Dickens and Elisa can publish the sums of their parts, only the sums, not the individual parts they got from and they have to, and everybody can add all together, and they have to get to 0. If they don't get a 0, anyone has lied about the parts sending to one of the watchmen. Okay, let's just skip it. There's a problem here in the scheme about the disclosure. There could be a conspiration of 2 people and saying, okay, we exchange an additional key, and we add this key to the message. We add this key to the round message, but do not add this key. Do not send this to Dickens and Elisa. And this works. Yes, there's a problem for the round key, but this works also for the original scheme from David Schaum. So this is still a problem. So you can do things like only 5 out of 10 watchmen have to agree to disclosure the message, thingy like. It's also possible. Okay, yeah, both schemes, my watchman scheme and the original one, are insecure against conspirations. But the advantage of the watchman scheme is that you do not have to contact the people afterwards, because the watchmen hold all the information needed to disclose the message, and no conspiration can be formed after the message has been published. So there are a bit of advantages. I think no disadvantage. So, well, okay. Anyway, so this for the literature. If you want to read something, the original paper is really good, and Andreas Pitzmann and Birgit Pitzmann also did some research about this. You can contact me if you want to participate. I I would really look forward to some people of, as example, Jabber, who want to integrate this into Jabber or into Silk or Circ, or maybe into a media wiki would be really cool, some PHP people. Okay, questions?
Hello? Yeah. With Java, wouldn't you need server-side support, or could the clients make it out themselves?
What do I sound?
If you implement this into Java clients,
Yeah.
wouldn't you need additional server-side support, or could the clients do that themselves? I'm not that technical into
The current
Java.
implementation uses a server, of course, because everyone sent the messages to the server and so on. But the idea I had with the serverless setup is that you just be able to publish something to any server who accepts something to publish, and then
So you could do this with publish subscribe extension
publish subscribe extension
for
Don't know.
Java? Okay. Yeah, thank you.
I don't know. I'm not aware of some publish subscribe extension. Okay.
I was wondering, for the chat, how many messages do you send a second from each client?
How many messages per second are sent?
Yes.
Okay, the current round time is, I think, 5 seconds timeout.
5 seconds.
The next round starts if anyone in the chat has sent, and if you don't set for 5 seconds, then you will be locked out.
So we have a chat with 20 people, and one person can say one line every 5 seconds?
Yeah, something like this, yeah.
Okay. And what do you use as transport? Do you use over HTTP in the end, or
Sorry?
how do you send the messages to the server?
Yeah, well, the current implementation uses, I think, XML RPC because it was the first
Okay.
thing I made be working on a Java. You're really, really welcome to exchange this to something that don't uses base 64 and very large text. So I think there's of course room for optimization in it. Be aware that the Dining Cryptographers protocol will probably never get to a peer-to-peer protocol. So you will never really be able to send messages to a specific peer. But I like to use only applications where you send messages to all, because they are sent to all anything. They are sent to everybody anyway. And if you do peer-to-peer, then you get really poor performance in it.
I got 3 questions regarding the cryptography here.
Yeah.
I was unfamiliar with the Dining Cryptographers protocol before, so I have 3 questions. First of all, I understand that there is some man-in-the-middle protection after the initial Diffie-Hellman key exchange, but I didn't quite understand how that was implemented. If you could briefly elaborate on that, that would be appreciated. Second, I don't understand how authentication is done. I mean, the first question is about, okay, how do you make sure that, assuming you have Alice, Bob, and Charlie, that only the keys are only known to A, B, and C, and not to Melis or whatever? And the second question is, how do you do authentication? In other words, how can you prove that Alice is really Alice? And the third question is, do you have a real-world scenario in which this protocol really is an advantage over existing approaches?
Okay. So the first was. Okay, I start from the last. I think those 2 applications are a start. So the chat thingy maybe not really chat, but maybe some kind of whistleblowing. So in a big company, there could be a Dining Cryptographers chat, and somebody could enter. Okay, I'm the guy next door. Each time I see him, he hits me in the bottom or something like this, and so you get some whistleblowing. Or as example, the police is also participating in a chat together with every people in Germany, and somebody can say, okay, I think there's a terror attack next week in Berlin airport. So you have really low volume, but you need really, really strong anonymity for this. So, and the second thing could be the distributed wiki. So where you want a closed group of people try to create something, but where you don't know where of the people did what part, maybe because of pressure, or because some people are in some foreign countries where they may not publish the information. And the second question about the authentication, it is basically the thing I showed with the GPG stuff. So if you log in and have GPG installed, then you are using your own GPG key ID as your participant key, and if you have this key ID in your key ring, you actually see a small small icon before your name, which means, okay, I verified the Diffie-Hellman key signed by the other party. Yeah. I'm hooking into the web of trust PGP providers this way. So you need an authentication thing beforehand. Nothing is for free, and I'm using the web of trust that comes with PGP for this. Of course, you can use any other method. So the first thing was after the what? Yeah, exactly this. So if you there's no protection of the integrity of the messages that comes from the protocol itself. So any active attacker in the middle could alter the message, or as example, the server could always throw away all messages you get and say, okay, the current round message was the following. So this the protocol isn't protected against these attacks. If you want to do this, you can use, as example, groups, group signatures, where only the participants have group signature key and so on. But the idea is not to give you some kind of authentication layer, but to give you some kind of anonymity layer if you want to publish something. Okay.
If you have unauthentic messages, or you don't even know that the message is integrity is assured, and you don't know where it comes from, what it is good for.
Okay, what you just said is that, for the microphone, what you just said is that you can add another layer on top of it, providing the authentication stuff. You can do this, you have to be a bit careful, because if you sign your messages with your own GPG ID, then of course the anonymity is broken.
I just want to say something to the question which was coming from there. One message per 5 seconds. There's another protocol which is the collision resolving algorithm, which can solve the problem that one message per second, 5 seconds. Then it's a little bit so everyone can just a message in that 5 seconds, but to resolve it, it takes the time how many message was sent. For example, 10 message was sent in 5 seconds. It takes 50 seconds to resolve the collision, but after the 50 seconds, all the 10 messages are in the chat, and in the next remaining 45 seconds, there can be sent other messages too. So it's a little bit better, and maybe it scales a little bit more, but it has to be implemented.
So what you just said is the problem of collisions. So if two people sending it at the same time, then you get a collision, you get the sum of the two messages. And this can be resolved into saying, okay, I can split this again later on if one of them sent the message again. So you do not lose anything of this. But still you have one message per 5 seconds. Yeah. Anyone?